So now we have PGuillon talk to us about flux-driven transport using the polarization method. Please, yeah.
All right, thank you. So hello everyone. Today I will speak about my work on flux-driven turbulent transport using the penalization method that I've done with Odgore and Sarada and Nicolas Tadorov. And I will first start by some general motivation. So a simple approach to turbulent transport, to turbulence in tokamak plasma is to consider fixed gradient systems in which we impose a linear profile, so constant gradient of density or temperature, and we look at the instability and the turbulence generated by this profile. And if we assume the perturbation to be periodic for a fluid model, we can have a simple implementation of such a system using a pseudo-spatial code based on fast Fourier transform. However, in this approach, the profile is considered to be frozen, and the turbulent flux generated by the instability never reacts on the mean profile. If we want to recover this interplay between turbulence and transport, we need to go to flux-driven models where we don't assume any scale separation between turbulence and transport. And in these models, we clearly can't assume that the perturbations are periodic along the transport axis. So for fluid models, we can't use a pseudo-spectral method based on fast Fourier transforms. Instead, we can rely on finite difference schemes, but they are less flexible, especially if we're interested in the model reductions. And to recover the flexibility of fast Fourier transforms and have a concise implementation, we developed Hitler, which is a flux-driven code based on the penalization method. And as a first test, we applied it to the flux-driven Hasegawa-Wakataniji system, but it can be easily modified to study your favorite fluid system. All right. So first, I will give some reminders about the Hasegawa-Wakataniji system and the phase transition that we can observe in the system. Then I will explain briefly how the code with penalization method works. And finally, I will show two applications to the flux-driven Hasegawa-Wakataniji system to test the capabilities of the code. Okay, so let's start with the classical gradient-driven Hasegawa-Wakataniji system, which is a simple model for 2D turbulence in tokamak plasma. So we take a 2D slab here, which is perpendicular to a uniform and constant magnetic field. And we assume that we have only a linear profile of density with a constant gradient kappa. And we look at the fluctuations of the electrostatic potential phi and the density n around this background linear state. So we have two equations. The first one is very close to the Navier-Stokes equation, where the electrostatic potential plays the role of the stream function fluid model. And the second equation is the advection of the density by the flow. And we have two linear parameters, kappa, which is the mean gradient of the linear profile, density gradient, and C, which is called the adiabaticity parameter, and which couples the two equations. And it's related to the dynamics parallel to the magnetic. Okay. And contrary to beta plane turbulence, this system is linearly unstable, and we remove the energy injected by the linear instability by adding some small-scale dissipation. And as a side note, we can decompose each turbulent field between a zonal part, which is averaged along the poloidal axis, so the y direction here, and the non-zonal part, which has a zero poloidal, and the x direction is called the radial direction. Okay. So now we can study the nonlinear behavior of the system and look at the transition between turbulence and zonal flows in the system. So if we look at nonlinear simulations for different values of the adiabaticity parameter, so C equal 0.01, C equal 1, and C equal 10. First, we will see the linear instability of the system at some point. And then the instability saturates in turbulence. And while for low values of C, we have this 2D turbulence chaotic state, for large values of C, the turbulence self-organizes into large-scale shear flows, which are the zonal flows, which are quasi-stationary. And then for very large values of C, we have this exotic behavior of flows merging, which I want to discuss today. Okay. More generally, depending on the ratio between the adiabaticity parameter C and the mean density gradient kappa, we have two regimes. For low values of C over kappa, we have 2D turbulence, and for large value of C over kappa, we are dominated by zonal flows, and the system becomes quasi 1D. And the transition between those two regimes is around C over kappa equal 0.1. And recently, we studied in detail the transition between those two regimes by seeing it as a phase transition between a disordered state, which is 2D turbulence, and a colder organized state in the sense of thermodynamics, which is the state dominated by zonal flows. And as in phase transition, we define, we use a control parameter, which is C over kappa, which we move to go from one regime to the other one. And as an order parameter to control the phase in which we are, we use the fraction of energy inside the zonal flow, which is close to 0 in the turbulent regime and close to 1 in the zonal flow dominated state. And then we try to investigate the presence of a hysteresis around the transition point C over kappa equal 0.1. So if we start a simulation here in the turbulent regime and we slowly increase C over kappa, we are able to transition into the organized state dominated by the zonal flow. And then when we decrease back C over kappa, we are able to sustain the zonal flows below the transition point. And our interpretation of this hysteresis is that zonal flows are like a crystalline structure, and we need some additional energy, some latent heat to melt the zonal flows, if you want, to go back into the turbulent regime. So it seems that the phase transition between those two regimes might be a first order phase transition. Okay, so that's it for the classical gradient-driven system. Now let's go to the flux-driven system, where the mean gradient of the profile will self-consistently evolve due to the turbulence. So if we take some given radial profile here in blue, which depends now on time, we can still define a background gradient by taking the mean slope of the profile between the two edges. And that way we get a linear part here in the green, where the mean gradient will not depend on time, because if the radial profile collapses like that, the kappa will decrease. And then if we subtract this linear part from the radial profile, we get a perturbated periodic part, which is just the zonal profile. Then we can write the total density of the system, which is composed of the linear part, the zonal part, and then the non-zonal turbulent part, which has a zero colloidal. And we can rewrite the equation of the density equation of Hasegawa-Wakatani for the total density. And using this equation, we can give the complete set of the flux-driven system. First, we have the vorticity equation, which here remains unchanged. Then, from the total density equation, we can extract the equation on the non-zonal density fluctuations, here, where you see that kappa depends on time. And if we take the colloidal mean, so the y average of the total density equation, we get the transport equation on the radial profile, where here gamma is the turbulent flux, which is the colloidal average of the non-linear term here. And we can add a source term and also a diffusion term due to neoclassical collisions. And bear in mind that there are no scale separations between these two equations that just been decomposed from the total density equation. And we could also add a similar equation to evolve self-consistently mean equals the velocity profile using the vorticity equation, but it's practically more complicated to do the decomposition, so we left that for the future versions of the code. Okay, now let's see how to practically simulate that using fast records. The aim of doing this decomposition that I shown earlier is to get from the radial profile a linear part, which will give a constant background gradient, which just now is self-consistently evolving in time, and then periodic perturbated zonal part. But you see that the zonal part, even though it's periodic, its derivative is not, because here it's a positive negative. And because we need the zonal density derivative to solve the equation, we can't still compute its fast Fourier transform. So to do that, we decompose the total radial domain into a physical domain here in the center, at the edges of which we will decompose the profile at xd1 and x2. And then at the very edges of the domain, we have two buffer zones here, in which we will modify the zonal profile so that all its derivatives become periodic and we can compute all the Fourier transforms that we want. And because this modification is artificial, we need to damp the fluctuation inside the buffer zone, and this is achieved by the penalization method. So very quickly, to modify the zonal profile, we multiply it by this gauge function, which transitions smoothly from 0 at the edges to 1 at the center. This is what we get. Here it remained unchanged in the physical domain, and at the edges, now the profile is completely flat. So all the derivatives are periodic, and we can compute the Fourier transform. To damp the fluctuation inside the buffer zones, we use the penalization method that was introduced in this work and later used for hydrodynamic and magneto-hydrodynamic turbulence. And it consisted adding the following term, where here mu is a very strong large coefficient, h is a mask function which is 1 in the buffer zones and 0 in the computational domain. So here in red, you can see 1 minus h. And this term makes any field A to relax exponentially toward a buffer limit in the buffer zone. And if we add the two following terms in the equation, we make the velocity and the non-zonal density fluctuations to go to 0 inside the buffer zones, while the radial profile will converge toward a buffer profile. And here is just to show you that the penalization starts as soon as we get inside the buffer zone, while the modification of the zonal profile to make its derivative periodic here in blue-violet is only done at the very edges of the system, so that fluctuations don't see this artificial modification. All right. Finally, we want to apply some non-trivial boundary conditions to the system. And what we choose to do is to fix the density profile here at the right boundary, while letting it evolve freely at the left boundary due to the particle plane. And we can't use the penalization to fix it here because the mask function is 0. Instead, we use a narrow Gaussian sink centered at xd2, and we just have to account for the sink inside the particle budget. Okay, so that's it for the basics of the code. And now, to test its capabilities, we apply it to the flux-driven Hasegawa-Wakatsumi system. And the first study is profile relaxation and turbulence spreading. So we start by the following density profile here on the top left corner. And this density profile is very steep here on the left and very flat on the right. So we expect the linear instability of the Hasegawa-Wakatsumi system to occur mostly at the steep part, which happens. Then we observe a local flattening with the formation of density holes and bumps, blobs that you can see here. And then these blobs become themselves chaotic, and they form turbulence, which is first localized to the left part of the domain and slowly propagates towards the right part until it touches the right buffer. And while it happens, the density profile collapses because there is no particle source here. And in the end, the system is dominated by zonal flows. So we can also look at the time function of this simulation in just a second. So here we see rapidly linear instability, the blobs, then the turbulent activity located to the left part, which slowly spreads to the right. And then, while the profile collapses, and then if we go a bit further far, we see that now the system is dominated by zonal flows and the profile stops collapsing. Okay. So let's study that more detail using a 4,000 square resolution simulation. So this is the initial profile. Then after some time, we get the local flattening of the profile due to the density holes and bumps, which can be seen as an avalanche sometimes. Then we can see that the profile is completely turbulent on the left, while the right part of the domain is still at rest. And while the profile collapses, the turbulent region extends to the right until it touches the right buffer. We can also look at the radial profile of the turbulent kinetic energy. Here it's a Y similar plot. First, the energy is located around the steep part, then it saturates and slowly spreads to the right. And we can look, use this energy profile to track the position of the turbulent front. So using some proxy here, it corresponds to the circles here. And if we report those circles on the density profile, we see that it corresponds to the boundary between the turbulent part on the left and the right part, which is still at rest. So now we can look at the spatial-temporal evolution of the turbulent kinetic energy profile. So here it's the time, and here it's the x-axis. And you see that we have first this fast propagation of the front, and then a slower propagation. This is what we get for our proxy for the front propagation, which works quite well. And by this gray line, I note the time at which the front reaches the right buffer. Then we can also look at some linear properties, linear parameters of the system. So we can define a mean background density gradient between the left part of the profile and the front. And we can compute the corresponding growth rate of the linear instability. And we see that it decays according to some power law. And when it reaches the right buffer, it decays also, but according to some slower power laws. All right. So to study a bit the consistency of the observation in the code, we wanted to reproduce the front propagation using classical 1D models for profile relaxation and turbulence spreading that have been used, for example, in works. And here we have two equations, one on the turbulent kinetic energy, where we have a linear growth rate which depends on the local gradients of the profile. Then a non-linear saturation term due to turbulent saturation. And finally, a spreading term, which is in form of a non-linear diffusion term, where the diffusion coefficient depends directly on the turbulent intensity. And then for the radial profile, density profile, sorry, we have a similar non-linear diffusion term with the same kind of diffusion coefficient. And note that we could also have written the turbulent kinetic energy equation that way to study bistability. So the spreading of turbulence inside linearly stable region where the growth rate is negative. But in our case, we don't have any linear threshold, so the growth rate is always positive or very close to zero in the flat region. And we could also have included the effect of zonal flow shearing on the turbulent energy. But in this simulation, the zonal flow level remained low, so it was not necessary to include it. So we have three parameters, the nonlinear separation, chi and d. And we tune it manually from the DNS, and we run the 1D model. So this is what I show here. So in blue, it's the DNS, and in red, the 1D model. And you see that the evolution is not exactly the same, but they behave similarly. And the front propagation mostly seems to be quite similar. So indeed, we can look more closely at the front position as a function of time. Here it's in log plot and the velocity of the front. This is what we get for the DNS with the first fast propagation and then the slower propagation that we see also for the velocity. We can compare with the 1D model, and we see that it seems to match. The DNS for both front position and velocity. And particularly if we compare with typical diffusion estimation, so square root of t for the front propagation, you see that the front seems to propagate both in the 1D model and in the DNS slightly slower at t to the 0.4. And the velocity estimation seems to be okay in the slow spreading time. And one pending question is the relevance of this spreading term here. So we try also to cancel it. So taking chi equals to 0, and all the other parameters stay the same. And this is the green dashed line that we see here. And you see that the behavior is slightly different because first, the profile does not propagate as far as in the DNS and the original 1D model. And also the power law here is different. It's more steep, closer to the diffusion where it's actually different. And if we want both DNS and 1D model without spreading to match, we have to multiply the density diffusion by 10 until we don't get the power law, correct power law that we observe in the DNS. So here in the flux-driven Hasegawa-Wakanen system, it seems to be important to include the spreading term if we want to have the same front propagation with the same turbulent diffusion type. Okay. Finally, we can discuss the final state of the system, which is dominated by zonal flow. And to understand that, we can think back to the phase transition from the turbulent state to the zonal flow dominated state that I discussed at the beginning for the fixed gradient system. Here, in the flux-driven model, C is a constant. However, kappa, the mean background gradient of the profile, changes with time because the profile collapses. So here I show C over kappa as a function of time in the dashed green curve. And you see that it starts below 0.1 and it goes towards 0.1. And when it's close to 0.1, the zonal flow level here, in red, starts to increase. And then once zonal flow dominates the system, they suppress the turbulent transport, so the profile doesn't move anymore. And so it seems that if you start a simulation from the turbulent regime and you let it evolve without a source, you will end up into this marginal state dominated by the net flows at C over kappa close to 0.1. Okay. The second study that we can do to test the code is to see what happens when we put a particle source. Particle source. So I start a simulation with the following initial conditions. So you can see here the density profile. And I let it evolve until I reach a turbulent state here. And this is my reference simulation because I don't put any source. So the source amplitude alpha here is equal to 0. And here I show also the zonal fraction, fraction of energy inside the zonal mode. Then taking the same simulation, I will add a low amplitude particle source localized to the left edge. Then a moderate source amplitude here. And finally, a strong source amplitude here. So we can briefly look at how the system behaves if it wants to start. So first, all the simulations are the same because there is no source. And then I activate the source. And you see that the main observation is that without source, it will relax until it forms turbulent flows. And when we have the source, it behaves completely differently with lots of turbulent activity. And the main observation for those three simulations is that we see the profile oscillating. And this is due to a competition between the source steepening the profile and the particle flows generated by this steepening, which drives the particle away from the top of the profile. So in some sense, we can make a connection to what we observe in some pile models in self-organized criticality, where we put sand on top of piles, and at some point the pile collapses because we reach a critical point. And seems to be a similar activity. Okay. So let's look at these simulations a bit more in detail. So here I plot the net outward particle flux. Here the fraction of energy inside the zonal flows between 0 and 1. And finally, C over kappa. So this is the reference simulation without any source term. And you see that the flux slowly decays towards 0. The fraction goes to 1, and C over kappa reaches a value close to 0.1, and then does not evolve anymore because we relax toward the state dominated by zonal flow. On the contrary, here, if we have the strong source amplitude, we have a very low level of the zonal flow, and this is because we steepen the profile very quickly, and we never form zonal flows, and we are in this strongly turbulent state, okay, way below the transition point. Now, if we look at the low source amplitude simulation, you see that there is this oscillating behavior of C over kappa, because here the profile relaxes, then it's increased by the source, because it's steeper, it generates some flux, so then it relaxes, and so on and so forth. And this is because, as I said, we have this competition between the flux making the profile collapse and the source steepening the profile. So, some sense similar to self-organized criticality model. But because here we are at the onset of a first order phase transition with the hysteresis, we might have what is called self-organized bistability, but it's a preliminary observation. We need to characterize that further. What's interesting though is that at T around 3000, we start to form strong zonal flows, and then because it suppresses the transport, the source can efficiently steepen the profile without generating too much particle flux. On the contrary, for the moderate source amplitude, we never form those strong zonal flows, and it remains below the transition point. And both simulations end with roughly the same mean value. And this last observation is somehow similar to what is called profile stiffness, which is observed experimentally. Where close to the marginality, we can observe with very similar mean gradients different turbulent intensity. And in our case, for the low source amplitude in green and the red source amplitude in, for the low source amplitude in green and the moderate source amplitude in red, we see that there is a factor 2 in the turbulent level, while the mean gradients are very similar. And in our case, it's due to the fact that we have really different zonal flow levels, and because we are close to the hysteresis. So then the extension of this observation should be studied. Now, we'd like to study the extension of this observation to other systems. Okay, so now I'll conclude. So we have developed this PFLARE code, which uses the penalization method to do clock-driven simulations using fast Fourier transforms. And the code is open source and available on GitHub. And because it's very flexible, it can be easily adapted to other fluid models like fluid ITG or even geophysical fluid models. And in the future, we would like, for example, to use it to study the electron transition if we had a mean incomplete profile or study some reductions, some model reductions. To test the capabilities of the code and check that there was some physics inside, we use it to study the profile relaxation and the turbulence spreading in the flux-driven Hasegawa rocket model. And we managed to reproduce it by classical 1D model of coupled equation on density and energy profiles. And here we tune manually the parameters from the DNS, but in a more systematic study, we could optimize the parameter directly from the DNS and include zonal close sharing and other effects. And finally, we also observe what happened when we put particle source. So we observe some behavior similar somehow to some file models in self-organized criticality, or maybe self-organized by stability because we have a hysteresis. We need to characterize that further. And finally, due to this hysteresis, we think that we observe a profile stiffness, so similar mean gradient, but very different turbulence intensity. And in our case, it's due to different zonal flow levels because we have this hysteresis in the fixed gradient system. So, and that's all. Thank you very much.